So it's my pleasure to introduce our next speaker, Professor Natalia Rozhkovskaya from Kansas State University. So she will talk about action of W1 plus infinity and WB1 plus infinity on generating functions of symmetric functions. Please.
So first of all, of course, I would like to thank the organizers for making this wonderful conference, and it's a great honor to be invited to speak here. Also, I would like to thank the Institute for the hospitality, and I'm sure that there will be more wonderful meetings where people meet and talk different interesting things here in the future. So I would like to talk about action, combinatorial picture of some action of algebraic structures. And the work which I would like to share today is the joint work with the PhD student from Kansas State University, Caleb Fernelius. This is the object, the algebraic object, which we would like to discuss today. Let us consider a circle, and let's introduce a coordinate on the circle, which we will denote as t. And let's look at complex regular differential operators on this circle. And there are many ways to introduce a basis in this Lie algebra. One of possible ways is to take monomials of this kind, where we have powers of t, which can be labeled by, which can be any integer power, and also powers of this differentiation multiplied by t, which can be of non-negative integer power. And then Lie algebra, this Lie algebra naturally acts on the space of Laurent polynomials. And we can also introduce a gradient here by taking 1 power of t to the power s outside. And this action will preserve this gradient. So we have a bunch of vector spaces where our Lie algebra acts. And it turns out that there is a unique non-trivial central extension of this algebra, and it's commonly denoted as W1 plus infinity. And this is the object which we want to discuss today from different perspectives. So a little bit of motivation, just general words. First, this object appeared in mathematical literature in 1990s. It came from literature which was written by physicists on two-dimensional quantum field theory and integrable systems, because it naturally describes some symmetries of these integrable systems. And certain classes of representations of this Lie algebra are well studied, especially the ones which have nice manageable weighted decomposition. And for these classes of representations, characters are computed. And this is done, for example, in the papers which I mentioned here. And more recent interest, and which is kind of inspiration of the direction of our story today, but I'm not working in this field, it's just inspiration from other people to combinatorics, which we wanted to consider with Caleb, is coming from the connections of enumerative geometry with soliton hierarchies, such as Kadamtsev-Petuashvili, Korteweg de Vries, and BKP integrable hierarchies. So it turns out that some generating functions of intersection numbers, such as mentioned here, they are tau functions of these integrable hierarchies. So that means not exactly that they are solutions of these hierarchies, but after some change of variables and some manipulations, they can produce examples of solutions of, they do produce solutions of examples of, no, they do produce solutions of these hierarchies. And these are very famous statements and very active field of research. And in particular, many authors who study these tau functions, they use certain symmetries of these integrable systems, and some of them can be expressed through operators which come from this algebra W1 plus infinity and its analogues such as WB1 plus infinity. And another piece of information which is related to motivation of why we are discussing about action of W1 plus infinity on symmetric functions is the following. The classical result, which is due to Sato for KP hierarchy and for BKP hierarchy, that Schur functions are tau functions of KP hierarchy and Schur Q functions are tau functions for BKP hierarchy. And we can take linear combinations of those and also create other tau functions, but coefficients of these linear combinations must satisfy certain relations. And now we have generating functions of intersection numbers, and they are tau functions of these hierarchies. And that indicates that they can be expressed through Schur functions and Schur Q functions correspondingly depending on where they exist. And by the efforts of several research groups, these expressions of generating functions for intersection numbers through Schur functions and Schur Q functions were obtained. So here are at least some people who worked on this recently. And in particular, sometimes in some of these approaches, they use, again, the symmetries which come from W1 plus infinity to show how these expressions work. So maybe a little bit more I will mention during this talk a little bit later when I will have some explicit formula cited. And what we want to do today is to talk how W1 plus infinity and its analog act on families of symmetric functions. And we want to talk about this not coefficient by coefficient, but we want to combine everything in the generating function. So that will be our philosophy today for our story. So, so we define W1 plus infinity as differential, as a central extension of the Lie algebra of differential operators, but actually we want also to realize it as a matrix algebra using one of representations. And this is how we are going to redefine W1 plus infinity in the following steps. So let us consider the algebra of type A, infinite dimensional Lie algebra of type A, which we are going to denote as A infinity. And it consists of matrices which have non-zero elements in the strip of finite width. So only finitely many elements around the main diagonal are non-zero. So this is the analog of the infinite analog of GLN, which is needed for our purposes. And this is a Lie algebra, and Lie algebra structure here can be just inherited from a commutation relation of matrix units from GLN. So they generate this Lie algebra, and as a linear basis, as a linear space, this Lie algebra is where is it? Sorry, no. Okay, so here it is. So the elements of this Lie algebra are matrices where we just take one diagonal and have non-zero elements only on this diagonal. And then if we want to see what is the commutation relation between two matrices of this kind, which just live on two different diagonals. So the last line on this slide shows what is the relation. Again, we get some one-way matrix which is living on another diagonal. And again, let's take a central extension of this Lie algebra. Now we take generators which we are going to denote as Eij hat, and we take the relations, the commutation relations as in the case without the central extension, plus we add central element and multiply it by some cocycle here. And this is how the cocycle is defined. So there are different cases what it is corresponding to what kind of matrices we take here. So this is how we can define the Lie algebra structure on A infinity hat on the central extension if we just look at the generators. But what we want to do here is actually combine all generators and generating functions in big formal distributions. And the first question is, what are going to be these generating functions? What kind of creatures are these generating functions? Usually when we talk about generating functions, we have power sums in most of applications. But here we are going to have something more general, which is called formal distributions. Power sums or Laurent series, they are infinite only in one direction, and then they stop in the other direction. So here we allow to take formal sums which go infinitely in both directions. And these are going to call formal distributions. We can look at formal distributions with coefficients in complex numbers, in where operators acting somewhere in vector space. We can take one or two or several variables. So this is what we are doing. Formal distributions can be added. They can be multiplied by Laurent polynomials. But in general, if we try to multiply two formal distributions, we may run into problems because it will not be well defined. But still, in some cases, we have very nice situations where formal distributions can be multiplied. So in general, it's not well defined, but sometimes you can do this. And this is used quite a lot in, for example, in vertex, vertex algebras. And especially when we have formal distributions, those coefficients are operators acting somewhere, and action is local. Sometimes instead of multiplication, people look at normally ordered multiplication, normal ordered product. And they sometimes save the situation. They can make multiplication well defined, but still there are problems for combinatorics, for example, because this multiplication is non-associative, and also it's not always defined. So you have to have special properties of your formal distributions. Okay. And one of the formal distributions which appears in commutation relations is formal delta distribution. This is the definition. And one of the ways to understand what is this formal distribution is to think about it as a geometric series expansion in two different regions combined in one formal series. So here, this notation we are going to use for this geometric series. So it's the expansion of this rational function in the region where u is less than z by absolute value. And we can see that formal delta distribution, I have issues a little bit working with this. Okay, so this part is a geometric series expanding in the region where u is less than z by absolute value. And this is where z is less than u by absolute value. So these are two geometric series combined in one formula. And this is some formal sum. Of course, it doesn't exist as a rational function. Okay, and the name of the formal delta distribution comes from the property that reminds us of a delta function. Formal delta distribution can be multiplied by any other distribution. And if we do this, we can change the variable of this distribution. So here is a of z, and it can be a of u in the same product. So that's why it has this name. Now let's go back to our algebra A infinity hat. Let's take all our generators and let's combine them in one formal distribution. So the coefficients here, I and j, they go through integer numbers, all integer numbers. And then the commutation relations with the cocycle, which we wrote a little bit earlier today, they actually become this commutation relation on these two formal distributions. And then also it is nice to see that the cocycle here appears as a geometric series. So it has this kind of interpretation. Okay. So now let's take the formal distribution which we just defined, this T of uv. So it has generators of A infinity hat. Let's differentiate it several times by the first variable and set the second variable equal to the first one. So what do we get? so we get the formal distribution of just one variable. And it is not difficult to see that it is going to be coefficients of Taylor expansion of this function. So it's easy to see that these are coefficients of this expansion. And also, it's easy to write down the coefficients of this formal distribution. So let's find what are these elements of A infinity hat. They're going to be given by this kind of matrices, infinite matrices. Again, they are sitting on just one diagonal, each of them. And here we use the notion of falling factorial, so in the coefficient. And then the commutation relations of in A infinity hat in terms of formal distributions immediately give us commutation relations for these new formal distributions. And the immediate benefit of this language is that we can see that commutation tells us that we get again formal distributions of the same kind. So we get here again the same kind of formal distributions. And that means that the coefficients of these formal distributions, they generate a closed Lie subalgebra in A infinity hat. And actually, this Lie subalgebra is going to be again W1 plus infinity. And let's connect our first definition with the second definition. So the coefficients which we defined for these formal distributions, how are they related to differential operators? So let's recall that we have these differential operators acting on the space of Laurent polynomials, maybe just on one graded component. And we have had the basis. And if we want to write down how an element of the basis acts on this vector space, if we introduce a basis, then it will be represented by this kind of matrix. And in this presentation, the coefficients of our formal distribution T L of U of our another definition of W1 plus infinity, they will correspond to these differential operators. So this is how two definitions are connected. And just a little bit more of advertisement of this language. Also, the commutation relations which we wrote down, they immediately tell us that inside of W1 plus infinity, we have a copy of Heisenberg-Virasoro subalgebra. So because if we look at commutation relations of Tk of U for k equals 0, we immediately see that this is commutation relations of Heisenberg algebra. So this is, the second one is Virasoro algebra commutation, maybe not written in the canonical form, but this derivative with respect to U of formal delta distribution, so this coefficient can be rewritten so that we get exactly the most known commutation relation for Virasoro subalgebra. And the last one shows that if we apply Virasoro algebra to Heisenberg one, we will get again back Heisenberg one. So all this is closed, so we have a closed subalgebra, which is Heisenberg-Virasoro subalgebra. And it immediately follows from the commutation relations on generating functions, which we wrote down a little bit earlier. Now, we want all that stuff to act on symmetric functions, and let us introduce notations which would be useful for us to explain what we are up to. So the ring of symmetric functions, let's say it this way, that these are power sums, and every element of this ring of symmetric function is a power sum which is invariant with respect to any finite permutation of these variables. And there are several symmetric functions which will be especially useful for us. First of all, of course, Schur symmetric functions, which are given by this ratio of determinant formulas. And they form a linear basis of the ring of symmetric functions. And we will we will express almost everything through complete and elementary symmetric functions and the formulas which will appear later. So complete symmetric functions are given by this sum of these monomials where the indices are allowed to be repeated, and elementary symmetric functions by similar monomials, but we don't allow the indices to be repeated. And of course, power sums, where we take kth powers of all variables. So these three families of symmetric functions will be of importance for us. And it turns out, and it's very useful, that any symmetric function can be written as a polynomial in either family of generators. So any symmetric function can be written as a polynomial in complete symmetric functions, or elementary symmetric functions, or power sums. And also, there is a natural scalar product, which so where Schur symmetric functions form an orthonormal basis. And once we have a scalar product, we can define adjoint operators by this standard formula. And then we can take operators of multiplication by different symmetric functions and look at their adjoint operators. For example, if we take operator of multiplication by power sums, the adjoint operator is going to be differentiation by power sums. So we have these together, PNs and adjoint operators. They create the action of Heisenberg algebra on the ring of symmetric functions. And for the other ones, if we know how a symmetric function is expressed as a polynomial through power sums, then we can easily write down the adjoint operator. Just instead of variables, we write down these differential operators multiplied by 1, 2, 3, and so on. Now, we want again to combine everything in generating functions and formal distributions. So let's take operators of multiplication by complete symmetric functions, operations of multiplications by elementary symmetric functions, adjoint operators for both families, and let's combine them in formal distributions. So these are formal distributions of operators acting on the ring of symmetric functions, on the polynomial ring. And the next thing that we want to do is actually to create a generating function for Schur symmetric functions. And this is how we're going to define it today. So let's take several copies of complete symmetric functions, of generating functions for complete symmetric functions, multiply them all together, and multiply by Vandermonde. Then all this together result is a big determinant itself. It's a formal distribution, actually it's a power series in variables UL through U1. And if we expand the coefficient, if we expand this in monomials in these variables, the coefficients will be given by, again, determinants, which are just a variation of Jacobi-Trudi identity. And that tells us that the coefficients of these formal distributions, they are either 0 or up to sign. Each of them coincides with one of Schur symmetric functions. So each Schur symmetric function here appears more than once, but each monomial has either 0 or Schur symmetric function. And more specifically, if you have a particular Schur symmetric function, it corresponds to the coefficient in this series with these indices, where you have to subtract all this, like go down each time at each next coordinate. Elementary symmetric functions correspond to these coefficients, and complete symmetric functions also correspond to these coefficients inside this series. And many properties of this generating function S of UL through UM for Schur symmetric functions, they are especially well studied with the help of vertex operator presentations of symmetric functions. And this vertex operator presentation was first mentioned in a book by Zelevinsky. They were called as Bernstein operators. And Naihuan Jin in detail described them and their properties in 1991. And here is the theorem which I would like to cite. Here is the statement which I would like to cite. So it is due to Xiaobo Liu and Chenglang Yang. And it does the following. So it is the very explicit formula how W1 plus infinity acts on Schur symmetric functions. Namely, here is one of generators of W1 plus infinity, one of the coefficients of the formal distribution which we defined. Here is one of Schur symmetric function S lambda. And this formula tells us exactly how to express the image through the basis again. So it gives us the coefficients and it gives us the indices of this expansion. And they used this formula and the formula which I hope to mention later to study so how to express the tau functions which come from enumerative geometry through Schur functions. So this is what was their application. And also there were some earlier works where people looked at action of different vertex operators and Virasoro algebra and Heisenberg algebra on Schur symmetric functions. And some of these papers are mentioned here. So what do you want to do here? So we actually want to do slightly different thing. The previous formula was about taking a particular coefficient acting on the particular Schur symmetric function. Now we want to take all elements of all generators of W1 plus infinity, combine them in one big generating function, and this is Tk of u. And combine all Schur symmetric functions in one generating function. And see how this formal distribution, this quantum field of operators acts on this particular formal distribution of Schur symmetric functions of vectors. So why do we want to do this? Because actually the language which is used here in proofs is the language of vertex operators, quantum fields. It's very natural here. So it's what happens behind all these calculations. And also because it gives some insight, a little bit more insight on how it works for, like in general, so how one big object acts on another one. And this is the formula, and I would like to give some a little bit explanations what is in this formula. So first of all, I would like to pay attention that it says that this action is represented as multiplication of something which I don't know whether I can call it logarithmic derivative. When k equals 0, it's just a logarithmic derivative. So something like a logarithmic derivative. The second statement is that the thing in green commutes with the thing in blue. So they commute with each other. And both of them are multiplication operators. So there are no differentiations here. We don't have to differentiate Schur functions here at all. So h, which is in green, multiply by elementary symmetric functions and e multiplied by complete symmetric functions and e multiplied by elementary symmetric functions. So I will try to explain this duality using the formula. Unfortunately, green maybe was not successful here because it looks almost like black. Here is, so what kind of duality here in this formula? So which we find kind of nice. So here is the generating function S of UL U1 is the generating function for Schur symmetric functions. So what it is a formal distribution. Okay, it's a formal distribution which has terms which consist of two things: the coefficient, which is a symmetric function, and the monomial, just a monomial. So in that sense, it is living inside of polynomial tensor polynomial, or like no, formal power. I don't know where it lives. Anyway, so it has. So it's like symmetric functions multiplied by monomials. And the formula which we have here, it says, okay, if I want to know the image of this operator on this stuff, I have to act separately on the symmetric functions multiplied by complete symmetric functions. And I have to act separately on these monomials multiplying by elementary symmetric functions, something like this. So there is some kind of duality in this formula because H and E, they have some dual role here. Yes?
So S is not symmetric in U.
It's not, no, it's not symmetric in U. Yeah. So let me show you the example what happens with this formula when we just look at the action of Heisenberg algebra, which is understood from different points of view and from different, so we can connect it with our knowledge with other things. So T0 of U is the generating function for generators of Heisenberg algebra. So what it says, so the formula when we just write down in this case is going to be the sum of two logarithmic derivatives. And the first one, it is known that if we take logarithmic derivative of complete symmetric functions, of generating function of complete symmetric functions, it's going to be a power sum generating series. So the first component, multiply each Schur symmetric function by a power sum. And the second component says, okay, so let's take this formal distribution which has formal variables u's and multiply it by this slightly modified geometric series. So, so the second part corresponds to operators of differentiation with respect to like Heisenberg algebra has multiplication and differentiation. So here differentiation is written just acting not as differentiations but as dual thing on the variables of this formal distribution. So there are no, you don't have to differentiate symmetric functions here at all, so only to multiply. Yes?
So it acts by multiplication.
Yes, it multiplication.
So it means that it's commutative.
They come, so they, no, it acts only, it's only for, applied only to this particular series. It works only for S, it doesn't act for all other stuff. So for Virasoro algebra, so how does this action look like? So again, we can see that, so this is explicitly the formula written for k equal 1. So here we have a bunch of logarithmic derivatives and higher logarithmic derivatives. And what it says here, so that we have to multiply Schur symmetric functions by power sums, and then we have to multiply this like series. So we have to multiply by this formal series here. If someone would be interested in how a particular coefficient here acts on a particular Schur symmetric function, what they would have to do here? They would have to find the coefficient of the particular monomial. And what kind of combinatorics it would involve. So here we would have to multiply power sums by Schur symmetric functions. This is usually done by Pierre rule, and maybe it should have to be applied a few times. So I do not think, and I don't claim that this way to compute coefficient by coefficient would be useful for the applications which in enumerative geometry, but it's some other way to compute how Virasoro algebra acts on Schur symmetric functions. So it's one of the ways to describe this. And also, since in general, where is it? In general, any higher derivative, logarithmic derivative can be expressed through power sums. Here we have that, strictly speaking, we express the action of all W1 plus infinity through the action of Heisenberg algebra. Again, I would not call it free field realization, but it's somewhere close in the half of it. Okay. I also never told how, in general, A infinity hat and W1 plus infinity act on symmetric functions in general. So that maybe answer your question before that. So if we have just any symmetric function, so how does algebra A infinity, these infinite matrices which live along the diagonal, act on this function? So here we have to apply a bunch of differentiations, a bunch of adjoint operators, multiplication operators, and then multiply by a geometric series all this result. And if we express all this formula in terms of power sums, in terms of Heisenberg algebra, we will exactly get the formula for vertex operator representation of jelly infinity hat, which appears first in one of the papers of the Data Jimbe Kashiwara Miwa in 1981. And W1 plus infinity, we wrote how it acts on a very specific generating function. But if we just try to apply it for any symmetric function, then we will have here this kind of formula. So we have to, it's like a Newton kind of formula, Newton binomial formula, and it is non-commutative. So here we have to be careful because H's and H adjoints, for example, they don't commute with each other. So in general, they don't commute. That's why that formula is also nice, that because there is a lot of commutative stuff. And now let's talk about B-type case. And the philosophy which we advocate here is the following. Of course, one can do the B-type case as a separate branch. Just look what we do in A-type case and then just do the same thing. So, and there are a lot of similarities. But moreover, we try whenever it's possible to use our calculations in type A case and use them in type B case so that we don't have to do the same work twice. And this is possible here, and you will see the traces of this in different formulas. So let us again go back to A infinity hat. So we go to the matrices which live along the diagonal, not go too far from it. And let us consider an anti-involution on this set, which is defined on the generators by this formula. So this is the anti-involution. We have a matrix of generators for those guys, and this is what happens with the matrix of generators when we apply this anti-involution. Oh, sorry, not matrix, formal distribution. And now let us take and create something which will be invariant with respect to this anti-involution. So let's take one copy of generating formal distribution for A infinity hat, another one, and combine them together in this expression. And of course, this expression will have invariance. So it will be invariant with respect to this anti-involution. So B should be inside, that's a typo. It is also anti-symmetric with respect of change of variables. And since we created it from A infinity hat, we can use the generating relations from A infinity hat that we already know. And we can just use them to find what are the generating, what are commutation relations between these two kind of matrices, formal distributions in this case. So of course there are four of them because there were two copies of generating matrix in each of them. And again, we can see that what we get here is closed under commutation relations. So we get, again, the same type of formal distributions. And the coefficients of TB of UV generate an infinite dimensional Lie subalgebra, which we are going to call O infinity hat. And inside this Lie subalgebra, we also want to consider some operators. And in this, we follow Johann van der Leur, Alexandrov, and Liu and Yang. They consider properties of these matrices. And we play exactly the same game as in type A. So we take our matrix, formal distribution of generators for O infinity, O hat infinity. Differentiate with respect to the first variable, and then we set the first variable to be equal u and the second variable minus u. We get a formal distribution with some coefficients, and we are interested in how the coefficients of these formal distributions act on particular families of symmetric functions. So we play exactly the same game, just slightly different objects. And in particular, this is the commutation relation between the zero level generating functions here. So it's some kind of variation of Heisenberg algebra here. So instead of Schur symmetric functions, the right object here is Schur Q-functions. And instead of H or E complete or elementary symmetric functions, there are these, I don't know how they call, maybe elementary Schur Q-functions. One possible way of them to define for this generating series, actually K will be only non-negative. So again, this allows us to refer our calculations to what we did already in type A. So this is how we define these coefficients. And then instead of the space of all symmetric functions, we have to consider a subspace which will be generated only by odd powers of odd power sums. And also it is known that these coefficients, they also generate this space. So we're going to call it B odd. And the Lie algebra O infinity hat acts on this space. Now, instead of Schur symmetric functions, we consider Schur Q functions. Maybe it's not the most successful definition that I could present here, but I just was out of time to prepare the slides, so this is one of the definitions. Schur Q functions, they are kind of Pfaffian kind of, they have kind of Pfaffian formulas, which may be not obvious from this definition, which I wrote down here. Nevertheless, I would like to cite again a nice formula, explicit formula, where you take one of these coefficients of this dB of u, dBk of u, and apply it to Schur Q function. And again, there is the recipe how you can do explicitly express this image through other Schur Q functions. So this is due to Xiaobo-Li, Charliang Yang again. And also, there were some particular cases in earlier works. And again, our story is to do everything in terms of formal distributions and generating functions. Now, instead of our formal distribution, which was generating function for Schur symmetric function, which we denoted as S, we consider this one. Instead of Wondermont, we have this kind of expression here, which is actually a collection of formal series which are expansions of rational function in the appropriate region. So we have here these generating functions for Schur Q functions, elementary Schur Q functions. And again, we take this series and expand it in monomials. And we get here symmetric functions, Schur symmetric functions, and monomials. So I already put this in color because there will be also duality in the formula which we will have here. So non-zero coefficients here up to sign are Schur Q functions, the classical combinatorial object which we know. And again, one of the main tools here working with this object is vertex operator presentation of Schur Q functions, which is due to Naihuan Jing from 1991. Okay, and here is our formula in terms of formal distributions generating functions of action here. And again, surprisingly, it is quite compact and nice and has duality. So here, what we have, so here are elements of W1 plus infinity B. So some elements of O infinity hat. Here we have collected all together in one generating function Schur Q functions. And if we want to act here on this formal distribution, we have to take the product of these two things, which are basically the same thing, but just in different variables. And instead of operator of differentiation, which we had in the previous case, we have this kind of differentiation operator. And again, there is duality here in action because green stuff acts on the Schur Q functions, on the coefficients, and blue stuff acts on the monomials. So we multiply by expansions of rational functions. And the last thing which I want to mention, again, I did not say how exactly O infinity acts on this space. This is how O infinity hat in terms of symmetric function acts on this, in general, any element of B odd. So we can take any element here. And if you want to know how an element of O infinity hat acts on this symmetric function, odd symmetric function, we have to do the following. We have to, again, multiply by some symmetric functions. No, so to apply a joint operator, so differentiate, multiply by these guys, multiply by coefficients of this expansion of this rational function, and also subtract this piece also multiplied by coefficients of expansion of this rational function. And here we use the same notations for adjoint operators of elementary symmetric functions, but here we also use that if we restrict these operators to this odd space, these two are going to coincide and the action is well defined. So we are going to get back the elements of this space. So the action of these restrictions is well defined here. So that's why we can write down here. And again, it allows us to use computations from A type to prove this formula in type B. And I think that's it. So thank you very much.
Thank you. Any questions, comments?
Thank you very much for the nice talk. I have a couple of questions. This generating function S, can you write it in terms of fermionic field?
Yes, it's actually the mathematics behind the proofs, yes.
I see.
Yeah, I just hid it because...
I see. Just by curiosity, how does it look like?
So you take fermionic fields of variable U1, so like fermionic field of variable U2, U3, so you take L of them and apply to vacuum vector, and then what we will get exactly will be this S.
I see. Sorry, a couple more. So you can also probably do type C and type D.
So I would be happy to talk to you because I don't know what happens at type C and type D.
I see, because I think Vandeler, Orloff, and Schroeter had some polynomials for type C.
So maybe I will ask you because I honestly just don't know even where to look for. I don't know what happens at type C or type D. So that's my gap in education.
And last question, maybe it's a bit more difficult, but how about beta deformation, some affine Youngian on Jack polynomials? Do you think?
Could you repeat again?
Some affine Youngian action on Jack polynomials. Or...
Do I know about this? No,
do
I
you
don't.
know? Okay.
I think there are experts here who know much better. Yeah, maybe you should ask them.
Any other questions?
Is it possible to extend these two cases to the Hall-Littlewood case?
Yes,
because
it is possible. Yes, yeah. So yeah.
Okay.
It was short answer. Yeah.
As in, it's written down somewhere.
Okay, I will be honest that I asked the PhD student to do this. So
Okay.
if you allow him to do this, that would be
Okay.
nice.
Any more questions? Comments?
There exist matrix-valued W1 plus infinity versions. Do you know
what to do with them? Not yet,
No.
but yeah, I would be happy to learn. Yeah. So I'm still learning.
Sorry, it's another defamation question, but W1 plus infinity, the Q version of that exists.
Okay, so you give me homework.
Okay.
Yeah, so I mean, I would be happy to talk and ask. Maybe you know more about this than I do. So I mean, I don't know about what are the properties. So I don't know. Yeah, so
Okay,
what would be the result there?
Oh, there's an answer.
Yeah, yeah. You don't know. Okay.
Yeah, I wrote a paper.
Okay. So I think our questions are morphing into discussions. Any more questions, comments? Then thank you, Natasha, again.